moving on. Let's talk about what's called conventional current. So originally, scientists thought that flow of charge was from positive charges. So if we have a battery here and a light bulb, it's just positive charges flowing from the positive end of a battery terminal to the negative end there. This is called conventional current. So in this case, it looks like it's flowing counterclockwise here against a normal clock hand. However, it was later found out that in a metal wire, it's actually electrons that would flow in the opposite direction. The electron flow is opposite to that, in this case, clockwise. But we still use the definition originally stated by Benjamin Franklin, which is current is a flow of positive charge. In all our equations, everything is always defined from a positive reference frame. So the tricky thing is it's true that electrons are the mobile charge carriers and they're drifting, but really, if you think about electrons moving from atom to copper atom, it leaves behind a positive hole going in the other direction. Either way, it's still going to work out the same to try to picture microscopically what's happening. Speaking of which, we're going to look at what happens on the microscopic level, which is called electron drift. This is a mechanism of how current actually flows. So the basic idea is a battery sets up an electric field, and then the electrons will gain kinetic energy because they can move. The tricky thing is, though, in real life, the electrons actually collide with the atoms of that conductor, like copper here. So here we have an electric field set up inside a wire, and current is a flow of positive charge. So what really happens then is electrons, since they're negative, they go against the field. And in real life, they kind of like just bounce around there. And that's called the drift velocity. And so what eventually happens is, as the electrons bounce around, the wire actually heats up. So if you ever notice, if you're running your phone like intensely with like video, or you're surfing the web, or you're sending a lot of messages, it actually gets warm after a while. And so that energy is lost to heat there. And so this drift velocity, what's crazy is it's really slow, thousandths of a meter per second. So in other words, the average time for an electron to drift through 1 meter of copper wire take several hours. So what's weird is when you flip a light switch, you don't have to wait a couple hours for your lights to turn on. And that's because instantly at the speed of light, an electric field is set up. So it's kind of like when you tilt a pipe. You don't have to wait for the water to first flow at the top, then the middle, and then the bottom. It all flows at once. So in this case, the flow of charge is instantaneous once the electric field is established, but the actual speed at which the charges move is actually very slow.